All right, so this is our presentation on our findings on Omaha natural gas. We are group 22. So the goal of our case was to look at data regarding natural gas and analyze some variables like production and consumption, imports and exports, seasonal trends, and environmental data of natural gas from the 1970s to now. In JUMP, we determined our 4 hypotheses would be: with the test of means, yearly usage would not change when comparing different variables. When looking at a time series analysis, we determined that there is no seasonal trend. There is a seasonal trend in natural gas usage across the years when analyzing them over seasons. When looking at a logistics regression model to see the relationship between usage of customers and a following year's numbers, we determined that it does affect the next year's numbers. And when looking at a multiple regression model to explain relations between 2 outside factors and the effects they have on daily sales, we determined that some factors and variables that would come into play would be heat and wind speeds. Some background on the data. The data is on residential usage of natural gas. The population of Omaha has risen over 120,000 since 1975, and public information obtained from an employee from the local utility company, MED.
All right, so some background information on the terms here. So heating degree days is how the company measures or helps predict how much gas they should buy. So heating degree day is 65, which is the temperature most buildings are kept at, minus the average of the max and minimum temps that day, temperatures that day. So up next is a decatherm, so that's a unit of energy consumption, which is equivalent to 1 million BTUs. A BTU is the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit, and miles per hour is obviously how fast the wind miles are, or the wind speed is moving. So for test of means, our hypothesis was that average yearly consumption hasn't changed since 1976. Our plan was to use JUMP to compare the means and see if that's true. Methods: first we were going to see if ANOVA works, and then we wanted to find out why did the results turn out the way they did. So first thing we did was test the data and see if it is normal. Obviously it's very normal, which is great. The data has been distributed since about 1976, so you have your warm years or cold years, and yeah, the total usage is definitely normal. Up next is we're going to see if the variances are equal. There is very little variance in the variances, which is great. You can see that they're pretty much well spread out. So we failed to reject the test, which means statistically the variances are equal. So finally, since the data is normal, the variances are all equal to each other, we can use ANOVA. So using ANOVA, we have an outstanding F ratio. So generally, if you have an F ratio of 1, that means your test is usually messed up. However, we collected a lot of data over the years, so we can pretty much firmly say that the average gas usage in Omaha has stayed the same for the past 40 years. So you got to wonder why. So the population's nearly doubled. Why would the gas usage stay the same? Big thing is technology. So in the 70s, they were still using things like this, a radiator, which is not efficient. And today you've got a lot more high-tech home heating devices, which makes a lot of the difference. And that way the average consumption per user is really decreased since 1976.
And for the time series analysis, we first look at the general trend over time. We can see that the natural gas usage follows a slightly decreasing trend, and before the 1980, there's a high amount of gas usage, and from the late 1990s until 2010, the trend is quite constant. And after the 2010, there's a downward trend occurring. And for the seasonal trend over months in a year, we have an extremely high usage is observed beginning in October through March, and the summer months from May to September, the usage is relatively low, and we can conclude that there's a natural gas usage has a strong seasonal trend within a year. And we conduct different models for time series analysis, and among the 6 models that we conducted, the seasonal exponential smoothing with 12 periods is the best one. It has the lowest AIC, MAPE, and MAE values, and the winters matters is also good because it has the same R square, but its AIC and MAE and MAPE values are just slightly higher. So we have some predictions generated by the best model, and we can see that the next month is January 2017. The monthly usage increases from nearly 4,700 to 5,400, and after the February it begins decreasing, and especially in April it drops sharply by 2/3 of the average consumption. So the monthly usage of the natural gas does have a seasonal trend.
So for the time series, we saw there is a seasonal trend, and moving into the logistic regression model based off of that, we wanted to see if there is a relationship between the mean usage per customer each year could correlate into whether or not there's a higher usage per customer the following year. And our hypothesis was that the yearly usage per customer does affect next year's numbers, and we were wondering if there's a certain usage number that would make usage the next year being higher improbable. So our findings, we found that the usage per customer has no significant effect on next year's natural gas numbers. And that's because the significant model numbers show that there's little correlation between the variables. The R-square value was 0.0155, which is absolutely terrible and doesn't really show us anything of significance. The chi-square value was also extremely low, and then the p-value was much too high to be able to say that the two variables correlate in any way. So more findings. I originally thought going in that there could be an increasing trend for natural gas usage that would come up among these two variables that would show that there is some kind of correlation, but there are no noticeable trends, and then the data was relatively scattered. The line did have a negative slope, however, but even looking at that, there's still an extremely low estimate for the variable itself, which indicates that an increase or decrease in that variable wouldn't greatly affect the model anyways. And then some other relevant predictors that either were in our logistic regression or were lacking that would probably help us get a more reliable model in the future. There are just too many factors at play to be able to correlate these two variables. The overall energy usage of customers could still be going up, but they might be using alternative energy sources instead of just natural gas. For example, coal, petroleum, electricity. The price could also be a large predictor that is missing in the model. So if we had price points for natural gas and for other energy alternatives, the R-squared value could have gone up. We just don't know. And then other possible factors could be the availability. So the overall supply and also government regulations on certain energy sources, and then also the social acceptance of energy sources and what most people are using at the time.
Okay, so here we have the multiple regression model. So pretty much what we were doing is we were estimating the relationship between the two the models and the variables. And we were analyzing the heating degree and then the wind. So the relationship between the two variables themselves obviously were good. You can tell by the predicted plot that it's an upward slope. And then you can also tell by the effect summary, which I will talk a little bit more about later. But we have a fabulous R-squared on this as a 0.95, and that's almost 1, so that's great. So the data fits the model very well. And then we also have a really good probability of 0.0001. So yeah. And then within this predicted plot, you can also see that outliers are non-constant, so they're kind of all over the place, but yet they're in a cluster around 0, so that's also a very good sign. And then you can also tell, so we separated then the heating and the wind separately from the sales. So you can also see the different variables as individuals. And from the heating, you can tell that there's a huge upward slope. And then with the wind, it kind of is a plateaued. It's a little bit of an increase. So both do play a part, but heating by far is the greatest variable that has the most impact.
So when looking at some external evidence about natural gas, we first looked at natural gas prices over the past years. Prices fluctuate over the past 25 years. In 2015, prices were close to an all-time low over the past 25 years. And prices peaked both in 2006 and 2009 and fell drastically after peaking in 2009 until 2014. And the next variable we looked at for natural gas was imports and exports over the past 25 years. For the imports from 1985 to 2007, there was constant growth. And then from 2007 to 2015, there was constant decrease for imports to the United States. And for exports, there has been constant steady growth from the 1970s until 2015. And in conclusion, we came to discover that the heat and wind play a part in the sales for natural gas. Omaha gas usage hasn't changed. The average usage per customer has actually decreased over the years. With time series modeling, the strong seasonal trend in natural gas usage was proved with in the winter gas prices or gas usage going up, and in the summer gas usage going down. Overall trend across the years studied was slightly decreasing. And for the 25-year history, we found after researching that natural gas prices fluctuate over the years, and imports and exports both had steady growth over the years. There were no correlation between yearly usage per customer and whether next year's usage will be higher or lower. That didn't have any effect on it. Due to the low R-square and chi-square and the p-value not being significant. Yeah, and that was our presentation on natural gas and the effects it had on Omaha's over the years.